You're listening to WMPG 90.9 Gorham, Portland, Southern Maine Community Radio from USM. Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang. Joining me, as always, is Bernie Ryan, DJ Star Watcher. How are you, Bernie?
Yes, hi, Sarah. Very good, thank you.
Bernie is our professor of the Astronomy Lab here at USM and our local protector of the night skies. Reach out to us at WMPG Scientifically Speaking at gmail.com or on Twitter at WMPG SciSpeak. And you can go to WMPG.org to find the last 5 weeks of archives of all of your favorite shows, including this one. Bernie, could you let our listeners know what is up in the night sky for this coming week?
Yes, certainly. I'd be glad to. So today will be Friday, June 11th, just over a week to go to summer. That'll be good. Okay, so it's going to be just past new moon. It'll be, so that's technically called a waxing crescent. It may be too thin to see, but you should be able to see it by tomorrow night. And then in the evening sky, we'll have Mars. Mars has been with us pretty much the whole year. You can still see that setting just before midnight. And Venus has joined Mars in the evening, so you can look for that. And if you like to get up early, you can see Jupiter and Saturn. Saturn comes up first around 4:30 in the morning, and then Jupiter comes up around 5 in the morning. So that's basically what's happening for this week.
No meteor showers coming up?
No showers. Toward the end of June and July, you get more showers. The Aquarids and the Perseids in August, and they tend to overlap, but really nothing in June. We got to wait a little more for those guys.
Thanks, Bernie.
Yeah, you're welcome.
And if you couldn't take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald, authored by yours truly. Not me, that's Bernie.
Yes.
Bernie, could you introduce our special guest for today?
Yes, certainly. I'd be glad to. Today we're lucky to have Stephen Goodfellow with us. I've known him for almost a year through just through Zoom. He has a master's in fine arts, and he's a professional artist, and he runs a group in San Miguel called Science Tech Nature, and I've been joining that on Zoom, and he does a really good job with that, and he's always excited about all different new things, and he has slightly different takes on science. I thought it would be great to have him on our show today. Welcome, Stephen. If you want to say some more about yourself.
So nice to see you, Sarah, and nice to see you, Bernie. Greetings, everybody. May I say what a pleasure it is to be invited to this get-together to discuss exciting things that are going on in the universe. Programs such as this is a doorway to pure, unadulterated awe, a drug that you are obviously addicted to, because otherwise you wouldn't be here right now.
I love it. So we have got a very, actually a really interesting show. Some of the stuff that I had never even heard about, really. But I think the first topic that we are going to delve into for today's show is the real nature of emptiness. Is that kind of the right way to describe it?
That's a great way to put it, Sarah. I always like to say, let us talk about nothing. It's like the English language is deficient when it comes to the topic we're going to talk about. So that makes it all the more fun.
Yeah. So what exactly do we mean by nothing? I feel like in kind of like theoretical physics, there's a lot of scientists who debate about how do you actually define what nothing is.
Well, that's a really good question, because it has changed so much over the past century. You know, it used to be light had to travel upon something back in the late 1800s. So they needed the ether was something it was a must have. So two guys, Michelson and Morley, they built a device, and lo and behold, they showed without a shadow of a doubt that the ether wasn't there, at least not the way that they thought of the ether. It simply didn't exist. And so for the next, until the 1920s, this was very popular. People would look out into the sky and say, well, out there, that's a vacuum. And that became the sort of, the modus operandi, and scientists sort of said, yeah, that's a vacuum. And then we started to see quantum mechanics come along, as well as observations of the sky. And they started to realize, well, no, it's not a vacuum after all. Especially the quantum mechanics definitely was leading the way with that. And they said, well, it's definitely not a vacuum. And then, of course, on Earth, in terms of planetary experimentation in laboratories, we tried to make absolute vacuums and realized over a very short period of time that you could get very, 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 very close to a vacuum, but you couldn't get to a complete vacuum. And that has had huge ramifications. And one of the things that I find so exciting, I found this article a short while ago about the Casimir effect. That's it, the Casimir effect, which is really fascinating. The basic idea of the Casimir effect is that if you're out in absolute, the thinnest of space, the best vacuums we can produce here on Earth, and you put two plates together, really, really close together. So what happens is they'll not allow larger wavelengths to get into between those two plates. And so they have to stay on the outside. Well, what happens is, because those longer wavelengths can't get on the inside of those two plates, it really is basic physics. Higher pressure on the outside, the plates slap together. And that's the Casimir effect. And that was basically a theory, a hypothesis until recently, until some bright boffins, that's the English expression for scientists in the East End of London. Some bright boffins decided to do an experiment and say, let's produce the Casimir effect. So they produced it as close to a pure vacuum as you can get. And lo and behold, the plates slapped together physically. They did work. They did work in a vacuum. Now, what's the implications of that? That's what's so delicious. The implications are, there's nowhere in the universe that has a vacuum. It is all under pressure to different degrees. We've got lots of pressure here in our atmosphere. It's a lot thinner on Mars. It's a lot thinner in our solar system. And it's a lot thinner when you get out into the intergalactic environment. But if you take a cubic centimeter of space and you look at it for a little while, you'll see that virtual particles are going through it. The background radiation is going through it. Regular noise is going through it, the radio waves. It's basically and whole atoms occasionally whiz through there. If you look at it for more than a second, an atom has gone through there. At least that's what I read. So what's so exciting about that is that it tells us that space is under pressure. Now, Bernie, you were talking about Nissan Harin. What did he have to say?
Well, he had an actual density for this vacuum energy, which is actually also sometimes called the vacuum catastrophe, because we were trying to figure out what dark energy was. And if you do the quantum value, you get this huge number. And if you do the actual value of the expansion of the universe, it's a tiny number. It's 10 to the 124th orders of magnitude off. I mean, that's the biggest mistake in physics ever. So one of them, I mean, it was quite right.
Yeah, and as I don't have a horse in this race. The one thing that I'm left with, from whichever school of thought wins this, they all agree that space is a fabric. And that's kind of what I'm sort of like into is something a little bit on the side from what they're talking about. So the question is this: if space is not empty anywhere, then the basic laws of motion, of gravity, the way things fall, is false. Now, on a day-to-day basis, that's fine. Hold on to the regular laws, guys. It's great stuff. It's not going away. You can send a rocket to Mars, and you don't have to worry about the pressure of space, but it's there. And the proof of it, if you could do this experiment, would be that if you were to roll Galileo's balls down a ramp, and the ramp was in an absolute best vacuum that we could produce, which of course is not a total vacuum. And you had the slide 50,000 miles long in this vacuum. The bigger ball is going to arrive, that bigger, heavier ball is going to arrive before the small, lighter ball. Or if you like, if you're on the moon, like the astronauts, you know, they drop the hammer and the feather at the same, boom, they landed at the same time on the moon. But if you go out into space 1,000 miles and you drop the hammer and the feather, the hammer's going to arrive first because space is not a vacuum. And that's big. That's absolutely huge. And I think to a large degree, getting to now we're getting down to nothing. So if space is a fabric, and you know, we're humans, we don't like to be limited to anything particular. Remember they used to say that airplanes couldn't fly faster than the speed of sound because they'd break apart, you know, and it would be a disaster. Well, they did, didn't they? They did break apart a few times, but they eventually got it right, and you know, they did fly faster than the speed of sound. In fact, several times the speed of sound. Well, here's the question: what if you can create an absolute vacuum, a nothingness? What would it be like? And if you think of it, imagine you could create a cavity like that. Well, the first thing that I can think of, just in basic laws of physics, is it would be round, because the space fabric that we live in, that the universe is, would be pushing on it pretty hard. And the next question is, what would be inside such a volume? Well, if we're talking about nothing, it would have no mass or energy in there. There would be no time. There would be no magnetic fields. There would be nothing in there at all. Now, you know, I think is it Voltaire who said nature abhors a vacuum? Well, maybe the space abhors a vacuum too. And that brings up some intriguing questions as, you know, does the universe allow for this to occur? And are these objects occurring? If they are occurring, we won't be seeing them because the universe is too busy pushing in on it. So what I would envisage is what you would see is an annihilation occurring on such a boundary. The question is, can you maintain such a boundary? And then the next question is, well, you know, the next thought is, the universe has been around for a long, long time, whether you believe it's been around forever or it's been around since the Big Bang, you know, and it's had a lot of time to figure things out. So if it's possible to produce absolute vacuums, then the universe is probably doing it. And I think as far as nothingness goes, I think I could go on from here, but I think this would then devolve into a 3-hour conversation that since we only have half an hour, I thought maybe this would be a good place to stop.
So are you suggesting that that there's not like one particular location where there might be an absolute vacuum, but that there might be little pockets of absolute vacuums that exist?
Here we go, Sarah. I'm afraid. Well, I believe that it's quite possible that they exist in our neighborhood, and I think that I think it's possible that our sun is actually is being very naughty, and it's doing just that.
How so?
Well, I believe that the sun may be manipulating plasma, super hot gas. Now I get very excited about plasma because they produce the most extraordinary configurations. If I could point to one in your mind, and that is, if you've seen any pictures of the loops on the sun, the solar loops, they're enormous. They're almost perfectly round. You can fit in next to each other in diameters, probably 5 or 6 Earths inside one of these loops. And you know, the sun has a crushing gravity of 28 times that of Earth's gravity, and these loops don't care. You know, here it is. It's like millions, possibly billions of tons of matter hoisted into the air into space, and they just hang there. They dribble a bit, but the actual magnetic structure remains completely devoid of interest about the sun's gravitational force. It's as if it didn't exist.
Hmm.
And so there are forces that plasmas can produce that are pretty extraordinary. I mean, you think of these loops are just dying entities that popped out of sunspots, and they just sort of hang there for a little while, and then they're gone. Just fading phenomena probably from what's coming from inside the interior of the sun. And one of and here I go. You asked the question, Sarah. So
Okay, so
now look what you've done.
Your fault.
So if we broke down what you were discussing in total, there's kind of three things that I pulled out of it. One is that space is not an absolute vacuum, that there is stuff there. And two, that we could potentially harness that power through the Casimir effect. And then three, what we were just talking about was that there might be places in space where there are absolute vacuums.
Sarah, that is very good. You managed to put that very succinctly, and I'm very, very pleased you did that.
I hope that's kind of my job. Is to try to make sense of it. So I'm curious. One, that space is not an absolute vacuum. That is 100%, like, everybody is in agreement with that.
That's a fact. I mean, that is agreed upon both from the old doddering physical science point of view and from the quantum mechanical point of view as well. And of course, we have spacecraft that have more than aptly proved that, at least as far as getting out to the sun's heliosphere. Mm-hmm. So that's pretty far. And the sun's heliosphere, I mean, talk about the new ether. Here's this shape that surrounds our solar system, that basically a large magnetic field bubble, and this whole bubble with us in it travels around the galaxy and has got a tail on it, probably, and it probably looks like a bit like a creature. And as it's moving along, a little aside here, it's colliding with galactics, with the Milky Way's space, and as it does so, all these little particles, whether they be on a atomic level or dust or larger rocks, which gravity does a pretty good job of dealing with. But as these are sort of floating out there, here comes our sun with its heliosphere, slams into it at a phenomenal speed and knocks off electrons and protons from these little grains of dust. Now they have a static charge. Now they'll travel along the sun's magnetic field lines and get gobbled up in the sun's. Would you believe the sun has an aurora on the north and south? Well, it pretty much must have, because our Earth has it, and Saturn has it, and Jupiter has it, and a lot of others, and we've seen it as well in satellite images. So this is, in a way, this is like the sun's digestive system, if you want to put it in a poetic light.
Yeah. So I'm curious about, if we can go back to the Casimir effect. So there's all these particles, any types of particles, right? You mentioned dust and subatomic, atomic, etc. We haven't actually been able to really harness this power.
Well, we have now. That little device,
the two plates.
The mechanics or scientists made, God bless them, it snapped shut. So we know that it works. We know that it works in a very, very pure vacuum. We know then that it's very likely, of course, the experiment is still is on the realm of hypothesis to theory, but I bet you my hat that if they perform the Casimir effect experiments, say outside our solar system, it'll snap shut. And if you do it outside our atmosphere, it'll snap shut. It does work. I mean that it does work. It produces, the closing of the plates is an activity of work, and that is the pinnacle of proof, hypothetical, theoretical proof, that our galaxy, our solar system, our universe, everywhere is a universe under pressure.
Hmm. And so I feel like I've read that there are some ideas that we could potentially use the Casimir effect to potentially power spacecraft through space.
You know, I love you for that, Sarah. You know, I remember a letter that Johannes Kepler sent to Galileo saying, one day we'll be able to take sailing ships to the moon. And I can just see, like Galileo's eyes rolling, and Kepler was right. And so are you, Sarah. They probably will be able to find a use for the Casimir effect. I don't know what that would be, but that it exists is enough for me. That phenomenon. It's kind of like going back to the I forget what the name of the guy who had lots of money, old English guy, put two big spheres together and pumped the air out of it and tried to have two horses pull it apart, and they couldn't do it. I mean, if I was a kid back then looking at that, I'd go, that is fantastic. That's fantastic. And the Casimir effect is like, well, it's two plates coming together, and that's fantastic. Where does it lead to? My little brain hasn't even begun to think about that. Sarah, I leave that to the brighter boffins of the world.
So then what does it mean for you? Um, to know
Well,
that I mean, I can see that you're very excited about it, but
yes. Well, again, we're going to talk a little bit more about the Webb telescope in a minute, but I will say that me and a guy here in Science Tech Nature, this guy Larry, I had a conversation with him not long ago. Well, 2 years ago now. That's not long, is it? And I said, Larry, no one has ever tried to see if an electrical discharge will deviate the path of a photon. See, photons do not have, are not affected by the electromagnetic at all. That is the dogma that we have grown up with, right from Hans Christian Ørsted into Faraday, Michelson, Morley, and onwards, is that, the photon is only affected by a gravitational pull. And I agree with that. I think that's true. But I think that what electrical discharges do is I think they produce that nothingness. I think they produce filaments. They massage space and open it up. And when it collapses, the collapse is not just a ordinary regular collapse, it's a gravitational collapse. And I think that if we can pass a laser past a sizable electrical discharge and see if the photon deviates. If it doesn't deviate, all's good with the world, we can continue on as we are. But if it does deviate, that suggests that there's a link using a plasma, using a plasma configuration that will deviate the photon. And if the photon deviates, it's a gravitational deviation. And that I find exciting.
Yeah, we discussed that a little bit. I had talked to Steve a whole hour a few weeks ago, and he had mentioned that project. And I was trying to see if there's any colleges that might be willing to offer him, some of the materials to maybe do that or something, so we could maybe work on that. But
I've had two close calls. One was as I told Bernie, I got an introduction to the University of Michigan Plasma Department. I need an introduction because otherwise I'm just a lunatic crackpot. So the introduction was from one of the foremost physicists who deal with the plasma world, Anthony Peratt, and so the guy deigned to listen to me, but it was the perfect storm. He was on the verge of retiring, and he says, to me, Stephen, this sounds really exciting, really exciting. I like this idea. But you know what? If I try and perform this experiment, I'll lose my retirement. I'll lose my pension. They'll kick me out of here. And the thing that brought Larry, my friend, into the idea of performing this experiment was, I said, go ahead, look through all the journals, go back in time, see if you can find any instance where that experiment has been carried out. And he went back to look, because he's from that world. His whole background is on flat screens and light and stuff. So he went back and he looked and he came to me and said, yeah, no one seems to have done it.
Do you know about any current experiments with the Casimir effect, just looking at the future, besides?
That's a good question. When I went out to dinner with Anthony Peratt, and I said to Anthony, he was at a lot of the nuclear detonations. They sort of brought him along. Hey, come along, about plasma. Come on, tell me what we're looking at. And I asked him, did anybody ever think to put a gravimeter near the explosion to see if there was any deviation of the space fabric towards the explosion? And I said, no, they didn't care about that. They had no time for that kind of nonsense. So, something may pop up in the future. I'm like I say, I'm trying it myself. I've got the laser, I've got the tripod, I've got a telescope site that is set up. I've got a neighbor nearby who will agree to let to use his wall about 400 meters away. And so and Larry's looking at me going, that won't work, that's stupid. But I said, Larry, we'll work simple, and then we'll do it your way. We'll get into the laboratory and do it in the real expensive, hard way of doing it. But let's see if the deviation occurs on a simpler level, So we try that. We'll try that first as soon as the damned pestilence has passed by, and we can take their masks off and get together again. That is a bugger, isn't it?
Well, that's exciting. Could you actually go into more detail about your setup?
Yes. Well, basically, it's very simple. I think anybody could, with any half a brain, could do it. You take a laser. You have a target.
What kind of laser?
I would use a ruby laser would be fine. Something that has polarized light is what you need. Mm-hmm. The next to the laser light, you want to have an electrical discharge take place. And there's not just any old electrical discharge. It's got to be a direct current discharge. One of the parts of my conversation with Anthony Peratt was, we were talking about, what happens with the plasma when it gets to start organizing itself, say, in what they call a dynamo effect. And he giggled, and this is the first time I ever heard him giggle. He says, well, then the electrons and the protons, they dance. And then, or basically the sort of mindset that is that the electrons and protons, they organize themselves into separate camps and then interact in a most complicated fashion. And if you've ever heard of plasmoids, they do this. So this is like a highly organized state of plasma. Lightning bolts. Lightning bolts are pretty interesting. You see them in slow motion. We haven't seen them slow enough yet to see what's going on inside of an electrical discharge. You've got protons flowing out of the ground, electrons blasting out from the clouds, and then they join together and they dance. It's when that dance occurs. When that dance occurs and collapses, that's what we want to have a look at. So you want the laser, you want a ruby laser, you want to have a DC discharge occurring, and you want an interferometer that's far enough away to where the photons, which can be recognized because they're polarized, that's polarized light, where the photons land on a target. First you do the target without the discharge, then you do the target with the discharge, and see what happens. Maybe nothing, maybe something.
We love when our guests are doing their own experiments. So
Well,
you'll
Molly, what's so exciting about it is this could be the plasma. You know, everybody's been looking for a unified field theory, and they're looking down in muons, you know, and the finer particles of the below the shell of an atom. But it might be more simple than that. It might be something that we're capable of on a you know, on a less sophisticated level.
Mm.
And if it's so, you know, we know that you can't produce gravity with liquids, and you can't produce gravity with solids, and you can't produce gravity with gas. But no one's tried it with a plasma.
Mm.
so,
Mm.
so that's why I'm interested in that. It may be the bridge between the electromagnetic and the gravitational.
Yep.
You need to come back and let us know how your experiment.
Yeah.
Well, I'd love to. I mean, you know, I've been wondering, you know, should I wear a silver bone through my nose when I go for the Nobel Prize, or could I keep my sandals on?
Yeah.
That was part 1 of our conversation with Stephen Goodfellow. Check out next week's episode to hear more, where we'll be talking about groupthink and discoveries of the James Webb Telescope that he thinks we will learn more about. You've been listening to Scientifically Speaking here on WMPG with myself, Bernie, and Stephen Goodfellow. Stay tuned for music, more talk, and more fun on WMPG. And from your favorite nerds, we wish you healthy bodies and clean air.